Uh, you want everyone to mute their thing or like,
Yeah, no, you can like if you have any like particular uh, thing to ask, you can unmute and ask in between also. That is not an issue.
oh, okay, okay. While you're teaching, we can be muted.
Yeah, yeah. Yeah, it is like you can interrupt in between also. It is not like this discussion only. It's not like uh I'm teaching or something.
Yeah, fine.
So okay, in this section, like this is what I planned for today. Like if it is not finishing, we'll continue tomorrow. So in this general search strategy, I think you guys have gone through uninformed search techniques, right? You might have already
Yeah.
gone through. So in
Yeah.
this, what I'm planning is just we'll briefly go back to search like that strategy, general search strategy,
Mm.
and then we'll move on to like these things like informed search. So like if anyone can like recollect the general search strategy, uh,
The uninformed search, no?
sorry,
Uninformed search, the general search strategy.
yeah, general search strategy does not like it is like a general thing. It is not like uninformed or it is not
Yeah.
specific to uninformed or informed.
Mm.
Like
Then,
you will initialize like a list, like a fringe they call it. We will
okay,
initialize
the
with a,
tree
like
search and
a
graph search.
yeah, like anything. Let it be tree search, let it be graph search. So we'll initialize it with the start node. Okay. So initially the list will be empty and will only have a start node. That will be the starting point. Like and then everything the other steps are like iterative steps. So this is like a iterative steps. Here we will like pop something, pop the next node from fringe. Then we will do a goal test. Goal test. What is a goal test? So goal test is like if suppose we are having a predefined goal, so then we will be checking an equality condition like if current node n is equal to goal or something. Yeah, that is like goal test can be a function actually. It is like a function of the current node. It will return one if it is like say goal is reached or like it is a very general thing. It should not be like you should not be thinking that it is just an equality check. It could be
Have
anything.
a small doubt.
Yeah.
Uh, so goal test in the sense like, for example, like if the say a particular node is in the fringe, it can be goal test, or it's like the one which is actually opening. So that which so exactly goal test is what, because like if the
Goal test.
element is in the fringe, it's
So suppose like this is like the starting phase, right? So let me take another case where you have like say one, two, you have n nodes already in the fringe. This is the fringe. So you have n nodes already. Now you based on some strategy, there will be some strategy on which to give priority. So that depends on which algorithm you are using. So based on some strategy, you will be selecting one of the node, and this node will be actually defringed. Actually, the term is defringed. Once you defringe, it will pop out from the whatever data structure you are using. So this might be a queue, or this might be a stack or something, priority queue, or it might be a min heap, whatever. So once you defringe that thing, it will be like the delete operation in whatever data structure that you're using. So it will come out, and then you will test whether it is a goal or not, like whether it is your target, whether you have reached the target or not. That is what I mean by a goal test. Like you will use some function like function goal test, and then you will pass on like pass this node, like the current node that you have like defringe f. And if this is like one, right, then you will return the path actually. That means your algorithm has stopped actually because you have reached the goal. This is what I mean by a goal test. So like practically like taking an example. So like in a grid, suppose like this is a grid actually. This is your seven. Like there was one particular one problem that we saw in the Telegram group, right? We are starting from the origin. Like each point we can go either up, we can go right, or we can go down, or we can go left. These are the possible like situations or possible moves, and we need to reach this particular node, like 6,7. So like there is like one. This is one possible path. Like you can go like this. So once a goal test basically means you are checking whether you have reached this particular point, goal point or something. So that is what is called a goal test.
So the defringed element is actually the goal element. I mean
Yeah,
the
you are
particular.
each time when you are defringing something, right? Each time, like it happens every time. Every time you are defringing something, you will test whether it is a goal or not.
Okay, yeah, got it.
Like whenever you are popping something from the fringe, like in the search tree, like let me draw the search tree first. Like this is a starting node. This is your starting node. So in the first iteration, only the starting node will be there in the fringe, right? So what will happen? You will take this node outside from the fringe and you will goal test. And if it is the goal, right, then you will stop the algorithm. That is it. The algorithm has finished. But it will only go to the further steps if this is not the goal. The second step is if it is not the goal, then what should you do? You should like generate successor. Successor means like whichever nodes that you can go from this particular node. So if you say you can go to say M, N, O, like you can go to three particular nodes. So this process of generating this thing, right? That is the step actually, generating successor. And like once you generate successor, you don't goal test actually here. Like you don't test when you generate. You don't do the goal test here. You just add them to the fringe actually. Means like you have okay, you have generated three, so you'll add M, N, O. This is the like entire general algorithm. Like this is the general search algorithm, which means this is applicable to informed, uninformed, like everything, anything you can think of in this way. This is the like exact thing that is being followed. Like the only difference is how do you decide which element to pop? Like pop a node from fringe, right? Like what is the strategy? Like which strategy you are using to select an element from the fringe? That is the difference between each and every algorithm, whether it is a informed search or uninformed search, whatever. The difference will come in this first step, like which node you are deciding to pop from the fringe. Everything else will be the same thing, and this is the only like exit condition. Like when you goal test and you reach the node, it is the exit condition. Or like when you don't have anything to pop, like fringe is empty. These are the exit conditions. Otherwise, you will continue in this loop. Is there any like confusion or like anything that you have to ask in this thing, in this particular?
No, it's clear.
It is
So
clear, right?
basically, the order in which the fringe is actually being defringed, so that is a strategy we can see, something like
Yeah,
that.
that is the search strategy. That is like where DFS, BFS, and everything is coming. So you might have already known this because you have already covered the uninformed search, right? But uninformed search,
Yeah.
you select based on the depth actually. Like DFS, what happens? You choose the deepest node each time. And in BFS, what happens? It is like last in, first out. The last node that you put inside, that has to come outside first. That is a strategy there. The only difference between DFS and BFS in terms of the general search algorithm is the strategy of popping from the fringe or defringing. Got it, right? We can move to the next thing, right?
Yeah. So, like, for example, you have something called bidirectional search, something like that. So, in that, like, what is the goal test? You don't have a goal test in that, right?
Yeah,
I mean,
bidirectional search. Bidirectional search is like a special case of this thing. Like special, like you are doing bidirectional search. What you're doing is you are applying this two times. This particular algorithm, right? This particular algorithm, you are doing from the you are defining like your goal node is also a start node. You are defining it like that. Like one version of this algorithm will run the
can
normal
we
way.
say like this for a bidirectional search? Like, I was having this doubt. So, whether like for goal test. So, for example, in bidirectional search, if the fringe has the, I mean, like the uh, I mean, one of the common nodes, then that is the goal test, something like that, or
Yeah,
it doesn't have goal test.
yeah, what you can think of is like two threads are running at the same time. Like you can think of it like that. It is not actually thread, it will be synchronized. Means it will not be concurrent processes. It will be like one after the other. So like one version is running like initial. This version is initialized using the start node, and this version is initialized using the goal node. And here instead of generating successor, you are generating the predecessor. And here the goal test is like that is a function that is like going like this goal test is like checking the intersection of maybe this is say thread 1, this is say thread 2. Goal test what it will do, it will check whether thread 2 is having like thread 2 intersection thread 1 fringe is having some element or something, like whether you are having
Yeah,
a common element in the
at
fringe
least
actually.
one. And
So that is like you can think of this bidirectional search as a special case of this general search algorithm.
BFS. We can implement BFS also with bidirectional search, or it's only like like you can implement DFS or something with bidirectional search.
Yeah, you normally implement DFS with bidirectional search.
DFS, DFS or BFS.
Sorry, you normally implement BFS with bidirectional search.
Okay, yeah, yeah.
Yeah, because yeah, that is how it will work. Otherwise, like you might take a longer time to for the fringe to say intersect.
Yeah, got it. Understood. I can.
Okay, so like now like this is like the first thing that I wanted to like recap only. And then the second thing is like why do we goal test when we defringe? Like we like in this general algorithm, right? We are already generating the successor, right? Like uh, think of the starting point. We are like starting with the first node, root node. This is the root node. We are testing whether it is a goal or something. Like okay, this is not the goal, so we'll generate the children of the root. Actually, this is like the level one children. So why are we not like when we are generating the children, right? Before fringing them, before infringing them, or before adding them to the fringe, we can do a goal test here, like whether test children. Like it might seem like it is more efficient, right?
Yeah.
Like instead of going to the next iteration, anyway we have generated successes. We can ask like okay whether it is a instead of going to the second iteration, like go like coming here and going back. Instead of doing that, we could have tested, right? So why this is not being done actually? That is like the critical point. So this thing can be done in an uninformed search actually. This can be done in an uninformed search. It will not affect the algorithm actually. It means it does not affect the optimality or something. Optimality is maintained actually, but it affects in a informed search. When it comes to informed search, right? There is a particular property in every informed search that we wish to maintain actually. So when we talk about greedy best first search, or like when we talk about a star, this point will come into picture. So at that point it will become more clear, but just now I am telling that if we goal test at this point, right, when while generating successor, if you are testing for the goal and we are terminating that particular search program, then what will happen is we will find the path, but that path might not be optimum. So this the only even if you like completely don't understand, the only thing you have to remember from this point is we are not goal testing here because we want optimum solution. That is the only thing. If we like if we don't care about optimum solution, then we could have done like goal test here also. Now why this will not like why if we do goal test here it will become unoptimal, this I will discuss when I talk about a star. It will become clear at that point, because if I talk about this right now it will become very unclear. So just you have to remember this point that you when you generate successor, if you are testing for goal, then the solution that you get will not be optimum. That is the reason we are not testing here. Okay, that was just like we'll come back to this point, but just I wanted to uh, like clarify, like when you're now internalizing this particular algorithm, right? Take into consideration that we are not goal testing here. That is that one thing that you have to take into consideration. Now like this is like the most important point I would say. AI search paradigm and data structure. So in data structures also we have seen search, right? Graph search, like DFS and BFS, like Digistrax algorithm and Bellman Ford. These things we have seen there also, right? In AI also we have seen the same thing. But why fundamentally there is a difference actually. It is not like the same algorithm is it is not the same problem actually. Even though the algorithm might look the same, it is not the same thing actually. So, anyone can has an idea already. Maybe you guys already have an idea like why this is a different. It is different from why this is a different from data structure search algorithm. Why the AI search is different. So if anyone has any idea regarding this, they can share it right now.
So you actually like in the data structure paradigm, like you will have another data structure which will be kind of having uh, the ones which haven't appeared. So that is the only difference between AI search paradigm and data structure paradigm. So you'll have, if there is a node that has already occurred, then that node cannot appear in the tree after that. So that is a fundamental difference, I guess. So
Yeah. Now what Bruce has told is how the strategy is differing between graph search and tree search, right? I think if I understand correctly.
yeah,
So now you told me about the difference between graph search and tree search. If graph you don't revisit a node, like in tree you can revisit. Like this never happens. Like here you can revisit. This can happen even in AI paradigm or data structure paradigm. Like this is not the defining difference, but yeah, you can say that data structure almost never revisits. Like you can say it like this, but AI can do both actually. AI paradigm can do both. Like it is not it is a difference, but it is not like the defining difference. It is like a consequence of a difference. Like there is some fundamental difference higher level because of which this has come into a picture.
maybe it's application level, something like
Yeah,
that.
it is
So
application
for
level. If you
example,
can think about it, that will be the best thing.
for example, you are driving a car or something like that, then you face an obstacle, and then again if you face the same obstacle again, then something similar to that.
Yeah, it is all almost you got it, I think. So let me the problem statement is the difference actually. The application. So in data structure, right, you already have the entire state space in memory actually. Means what I mean to say is that the entire network graph that you're searching, right, that is already in your memory. Means already in your primary memory. Means think of a data structure application, not a AI search application. Think of a data structure application where you will be using a search algorithm.
So yeah, so maybe phone number search, in contact search, something like that.
Yeah,
So when you're typing nine, so when you type, for example, 941, so I mean, what are the remaining contacts that could match this one? So maybe something
yes,
similar to that.
yeah. So data structure, yeah. What is happening is set of all states, right, or set of all nodes. This is something that you have in memory. Like in whatever data structure related graph that you can draw, in a data structure search problem, all these nodes are already in memory. Like either you have a adjacency list or something, or you have a adjacency matrix or something. This is already in your primary memory, and your search algorithm is trying to find the optimum path, or trying to search a path for minimizing some cost objective or something. Or say for example, yeah, you have a graph and you want to count the number of cycles, count the number of cycles in the graph. So you already have this thing in your memory, right? Then you are using DFS to count the number of cycles, right? You are using DFS to first count the number of tree edges. That is how you count the number of cycles, right? Then you count the number of back edges, and that is how you count the number of cycles, right? This application has the entire list of nodes already in memory. Like it might be an adjacency list, or it might be an adjacency matrix. But in AI search, the problem statement is like that entire state space is like very, it will be very huge. Like it will be like something like uh like it will be a very large number. Like for example, like in maybe how do I take this? Yeah, in Pac-Man, right? Like in this is Pac-Man, say. Yeah, you this is like a 10 by 10 grid of Pac-Man. So Pac-Man can have like there is only one Pac-Man, and there are like say 20 like 20 collectibles actually, like 20 points that you have to take, or 20 things that you have to eat. So like how much number of states will be there? The number of states will be like very huge, right? It will be like at least it will be like 2 power 10 into 10 or something. This many number of states are possible, right? So you cannot keep all the like possible number of states. All you cannot store the entire graph in memory. Like the entire graph is not in memory. What that means is like each time, right? Each time you have to generate the successor. You have to like from this point you have to apply some generating function to like generate. Okay, these are the possible next positions. Like you there is a generating cost is there, means it is not free. Like in data structures, this is something that you already have in memory. You can just go to your adjacency list. So suppose if this is node 1, this is node 2 3, you can just go to the first like the first linked list, and you can find okay already like this is something just you can look up in memory. Like okay, these are my successes. But in AI search, what will happen, there will be a function that will generate the successor, and it will have its own complexity. Say some like f of like it'll be like it'll have its own complexity. It'll be not something free. So for example, like in a chessboard, like given a position n, like this is a particular position, you have to generate like the next position. So you cannot go to memory and get the next position, right? You have to do some, you have to follow some rules. You have to like iterate over some variables, and you have to generate the next position. It is not something that you go to memory and take it. So, are you able to understand the difference, or should I go to take more examples or something?
Uh, yeah, able to understand.
Yeah, so like if you're able to understand, like can you like come up with an example of your own, maybe like in Pac-Man or like tic-tac-toe. Tic-tac-toe you can like reliably store in
Yeah.
memory because it is like
So
a very
maybe,
small thing.
yeah, maybe if you have say 3 cross 3 table, and maybe the number of uh, possible states that you can have to you have a goal state. At the same time you can have different states. For example, you can jumble say 1 to 9 elements in that 3 cross 3, and maybe you can move them, so you can have different number of states with respect to that. So but when you're stuck in a particular state, then you have maybe 3 or 4 possibilities for the next kind of state. So you don't have the exact map with you, but you have the next successor. So that is what you're meaning by generating function, I guess. So
Yeah, yeah. So in the AI paradigm, right? You are modeling the generating function. What you have, that problem statement that you're trying to solve, right? It will have a very clear rule or very clear definition of the generating function. But in a data structure, right, the entire graph will be very clear. Means the entire graph will be in memory, or the entire graph will be already like fetched from the secondary memory. Like that particular problem, right? The data structure search problem will not have a generating cost. Means successor generating cost will be big O one, or at most it will be big O log v or something. Means you just have to go to memory. You just have to go to memory and get the successor. You don't have to rely on a function to generate your successor.
so basically you have like a big O of b plus c. Maybe you can consider that as constant, or like
Yeah, big
how
O
do
of v
you?
plus is like the search. That is the entire search complexity, right?
Yeah, so that is what we are doing in like a data structure paradigm, right? Like for
Yeah,
example, we want to maybe from the adjacency list you want to take some element. So we are doing big O of v plus e. Is that a constant thing or is that something else?
Yeah, big O of V plus E is referring to the search. Like suppose you're like applying a DFS search or something. Big O of V plus E is referring to the entire search complexity. Like you have to go and refer to that particular adjacency list no less
Yeah.
than V plus E
Yeah,
times. Like
so we don't you don't have it as constant thing, right? For example, you want to go to the seventh element in the adjacency list. You have to go to the seventh element, and then you have to go from then. So is that a constant thing, or like what is that actually?
it is not a constant thing. It depends on like what data structure you're using to store your entire graph. But the difference is not in the like variable cost. Variable cost can happen even in data structure, or variable cost can happen in AI search also. But the fundamental difference is you don't have you cannot iterate over all the vertices, which you can do in data structure, but you cannot do that in AI search because you don't have the list of all vertices with you. You can only like given a vertex, you can generate the successor. That is the only thing you can do.
Yeah,
You
okay,
cannot say
understood.
for all vertices in graph, that you cannot do, because like the entire graph is like a monumental, it is like a very big thing in AI problems. Like it will be like all chess positions, like or something like all possible paths that a car can take, or all possible paths in a what in a Google map. Like it will be like a okay in a map, it can be reliably stored in a data structure. But suppose you cannot store your graph in a data structure, that is when AI searches, it is shifting to the AI search paradigm. But if
Yeah,
you are able to store your entire graph in a data structure somewhere in primary memory, that is like the data structure search paradigm, because then
so
you can like
actually,
ask.
so what is actually big O of v plus e? Exactly, what is this actually trying to tell us?
Yeah, in like big O of V plus is okay. Like are you talking about a particular like search algorithm in data structure or something?
No, actually, big O. So, for example, if we want to get, say, a particular, for example, for the seventh vertex, I want to get the fourth adjacent thing. So, so is that related to big O of V plus E or something
Yeah,
else?
big O of V plus is like the complexity for the entire thing, right? So there is a table actually. Like okay, this is related to data structures. So when you are implementing your graph in an adjacency list, and then you are using there are like two things that you can do. You can use a matrix or something, and then there are some operations that you that you like to see. Like you want to see whether u to v is like an edge or something.
Mm.
Yeah, so this will have some complexity, right? If you are using an adjacency list, this will have like the degree of u will be the complexity, I guess. And adjacency matrix, it will be v, right? Because you just have to go to that particular row.
I mean, why it is degree of U? I mean, like, for example, first we need to locate V, right? So for that you will have V, you will have V. The search will take V. Then from V it will actually take E. So that is why I was thinking we go of V plus E. So where am I getting? Where am I
No,
going wrong?
adjacency list is like vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, something like this is
Yeah.
an ordered
So
list. But then it is like a inside that this is sorted, this thing is sorted,
okay.
but inside each thing it is not sorted. It is like yeah, this is like it might be 3, 5, 2, 1, like something. So given a particular
Okay.
u, right, you can just go to u in big O one. This is big O one.
I was just wondering about that. How do you go in big O of one? Is that like some other implementation, or either you go by log v or something like that? So
No, no, this you don't have to. This is indexed, right? So think of u as
okay.
an index. This is an index. So like
Oh,
you want to get the fifth vertex. So the vertexes will be indexed from 0 to n. And
so
this that
indexed
this
in a
this
sense, everything will actually have big O of one. So that is what you
yeah
mean by
yeah
indexed.
given a
So
yeah, it will be indexed.
we are not. It's a different data structure altogether. So
Yeah, this
I
is like
mean,
a pointer list where like
okay,
you given the fifth vertex, I'll go to the fifth pointer and I'll just get the
okay,
head. This is
yeah,
this is like the
yeah.
head of the linked list. So
Yeah.
you can do that in a big O one. I'm not saying that this is how they implement, but given a vertex, right, you can go to the particular linked list in big O one, or particular
Okay.
row you can get in big O one.
Okay. Yeah.
Okay, so
So
like
what is the fundamental? Yeah, I understood this one. So what is the fundamental thing why we have like we don't visit the same node again in graph search, but in tree search we visit again? That is like the question that is actually having.
trees. Okay, I'll come to that point. Like let me like conclude this thing. So
Okay.
like this is something that you cannot do in AI search.
Okay.
Like you have to use a generating, like you have to use a successor generating function to do this.
Yeah, that means we can do it right. Like for example,
Yeah,
so okay.
you cannot do it from memory. That is what I'm saying.
Oh, okay.
This is
Yeah, I
not
got it.
stored in memory. You have to like rely on some function to do it. You have to call something which will generate the successor. Like you have to call f of u, and if like if that thing is generating a list, like say u w x y z something, you have to wait for this function to return this list, and then you can go and search in this list.
I have a small doubt. Like, for
Hmm.
example, you're saying f of u. Is it like something like you can call f of u at any point of time, or it is if it isn't at that particular location, if it is an element that is different at that particular location, then only AI search can be called the generator functions, or it can call generator function for any element at any time.
Yeah, you can like call anything at any time. Like you just have to give a particular valid state to a generating function. What that function will give you is a list of successors, means
Okay.
points where you can go from that. So like
Yeah.
think of like a program, chess program or something. I am giving a particular board position. Like I'm saying my pawn is here, my rook is here, my king is here. That what that function will do is give a list of all board positions which are one move away from the particular board position.
Yeah. Okay.
That is what a successor function is, or successor generating function is. But you cannot store the entire chess problem in a data structure, right? You cannot say if your pawn is here, okay, from this position I can go to, like, you cannot store this, right? This is like an infinite,
Yeah.
like it will take infinite amount of time, or infinite space it will take, or it
Yeah.
not
Understood.
infinite, but it will be like very big. This is the fundamental difference between AI paradigm and the data structure search paradigm. So like trying to call this very less time is like why they are like generating, how much times you are generating a successor, how much times you are calling this function is what AI people care about.
Yeah.
Yeah, but like how much time you are going to this adjacency list to get this particular thing, that is what data structure people care about. So they will like you say heap mim, like some minimum heap or something. They can use different data structures to represent the like graph, and they can like for different applications they can use a different thing. But AI search, it will always be like a particular generating function, and this complexity of this function you don't know. This might take some say it will not be like a function of n also. It will not be like, it will not be a function of
Of
number of
state.
nodes. It will be something entirely different.
Function of state.
Yeah, it will be a function. It will be a variable function that is not depending on the number of vertices in your structure.
So can we say it is function of state? So particular
Yeah,
state of any.
it is a function of a particular state. For some state, right, it might take a long time. For some particular state, it might take very less time. So it has nothing to do with how big your graph is.
Okay. Yeah. Understood.
So that is that is one thing that I wanted to keep in mind. One complexity. Okay, this thing. Yeah, this thing only just I was talking about, like why complexity is different in AI and data structure. So in data structure, you are optimizing for, like say the adjacency list or whatever data structure that you're using to represent the graph. Here your complexity, you are optimizing for calling the generating function less number of times. Like the lowest number of time you can call a generating function, that will be the lowest complexity. That is the difference here.
Okay.
These things are like just
So like we
I want
don't
to. Uh,
so like we don't care about the what is the time complexity in AI search.
the time complexity is related to how many nodes you expand. Like the number of nodes expanded will be your time complexity. Like
Okay, so like
num
we do know like till the maximum number of nodes it can expand up to like
like number of nodes expanded before you reach the goal. This is your time complexity in AI
okay,
search.
that will be our time complex.
Yeah, this will be your time complexity in AI search. And number of
Okay,
nodes I have to store in memory.
okay, that will be space complexity.
Yeah, this is the difference in complexity. Uh, this is the difference in difference with data structure. So in data structures, what was the for example in DFS or something? What was the time complexity in DFS? It is like big O V plus E or something, right? If I recall correctly, or no, it is. Yeah, it depends
Yes.
on how you are implementing. So it can be like if you are using a heap or something, uh, then it will be lower, I guess. It depends on what data structure you're using. But here, like in AI search for DFS, the time complexity is actually B into S, right? B into M they call, okay. And space complexity is also B into M, right? If I remember correctly. Where be like
B power m or bm. The time complexity is b power m, I
yeah,
guess.
B per time is B per M and this is BM.
Bm. Yeah.
Yeah, so this is what this is representing is time like this much nodes I have to expand. This is the number of nodes I have to expand, and this is like the number of nodes I have to store in fringe. But here it is not that thing, right? Here you are like you have to go to like recursive definition and you have to get the complexity. Like which it depends on which data structure you're using. Here it is not like that because the paradigm is different. That is why these guys are defining the complexity in different ways. Here it is like you can say complexity in terms of how big the graph is. This is in terms of the graph, right? The size of the graph. They're always using V or E. So V and E are like V is like the number of vertices and E is like the number of edges. So this complexity in data structure is in terms of V and E, means it in terms of the size of the graph. But in in AI paradigm, right? It is in terms of like how like the goal actually means or how in depth of the goal. Like you can say depth of the goal.
So maybe can we say branching factor and the depth of the code, something like
Yeah,
that.
branching factor and depth of branching factor because branching factor determines how much you have to call a successor function, like how bigger it is growing, and goal because that is how much you have to search. Because if you start to
Mm.
define AI search in this paradigm, right, this will not most of the time this will be like a gigantic number in AI searches. It'll be like say 3 power like some like AI search problems will be the graph size will be very big. So it will
Mm.
not you cannot express the complexity in terms of the size of the graph. You have to
Mm.
define the complexity in terms of on average how many children am I generating, like
So
on
it is
average
not
how
in
depth.
reality. the branching is going to be the same. I mean, for example, if we say b equal to 10, it is not necessary that all the branches needs to be 10, something like
No,
that. I mean,
that is only the theoretical concept, right? It'll never be 10. So you can think
okay,
of the worst case as the maximum number of children that I can generate. Any node can generate.
okay,
Like
yeah. So I
yeah,
mean,
the worst case you can think of it that way. Like the maximum number of children.
yeah,
It can
I
be
was
less than
having
that
this.
also.
Yeah.
And like S is like, or when they say B raised to S or something, or B raised to M or something, that is defining the depth of the goal, right? The shallowest goal or the optimum goal, like how much depth, how much deeper it is. So the graph might be even bigger than that. The graph might be bigger than the depth of, say, the goal. But AI does not care about that. AI paradigm only cares about the relative position of the goal and on average how much you are branching. The complexity in terms of branching factor and the position of the goal.
Hmm. Understood.
So this is like the complexity, like complexity when you're comparing with data structure complexity and when you're comparing with AI complexity. This is what you have to keep in mind. Both are different paradigms. They are not like the algorithm looks same, but they are applied in entirely different use cases, entirely different problems. You cannot use think of the same problem. Now we will move on to like the core things. These are like this whatever you can forget about whatever we have discussed up to this point. That was just maybe like to have a higher maybe higher clarity. I was just recollected all those things, but if even if you like don't understand, that is a fine, that is okay. But from this point onwards, you like if you have to pay attention, or you this thing is these things are important, like from what I'm going to say. So first thing is like an evaluation function. The script is legible, right? That colors I don't have to change, right?
Yeah,
Like maybe
like
if I
can you just increase the, I mean, the size of the pen?
okay,
So if
that
possible,
maybe I'm writing
like this will be fine.
to evaluation function.
White is fine.
Yeah, so evaluation function, what I mean is, so we had this general algorithm, right? I'll just copy paste this thing. And you have the fringe also. Evaluation function is like a some, yeah, e of n or something, where you take one element and you put it in this function. It will give you a value, and your strategy will be to choose node such that it will give you the lowest value. So your strategy will be choose from fringe to minimize e of n. Like if fringe is having say 1, 2, 3, etc. up to n. Like this, which node is giving me the lowest evaluation? I will first use that one. That is like the evaluation function. Like uh, so you will not be like iterating through the fringe and applying all the nodes one by one. What you will be doing is in the node itself, you will be storing the evaluation value. Like if say node S has an evaluation of 1, node V has an evaluation of 10, or node M has an evaluation of say 12. So you don't have to like each time you want to pop from the fringe, right? You don't have to go iterate over the entire fringe and calculate it every time. What you do is when you
So
put
this
it in the
happens
fringe,
when you, yeah. So this happens when, for example, when you branch out something, and when you're putting into the fringe, the moment you put it in the fringe, you actually side by side calculate the evaluation function, and then you add them into the fringe. If I'm not wrong.
yeah,
For
that is
example,
correct.
okay.
So if I want to be more like specific, this fringe will be a min heap or something, like some min heap or something. So when you put a node inside, right? When you generate a successor and add it to the fringe, right? At this point, you will evaluate it also, and then you will add it to the min heap, and then so naturally in the min heap, the lowest one will be the root. The lowest. This will be the lowest. So you don't have to, like, when you pop from the fringe, right? You don't have to go through each node one by one and just you have to evaluate. You just can take the lowest one and then you can goal test. So that is what I mean by an evaluation function. You evaluate and store it actually while you are generating the successor. You generate the successor, and then when you store it in the fringe, you are evaluating it. In this fringe will be like a list of nodes which have a corresponding evaluation. Evaluation can be anything. Don't think of if my evaluation is say cost or my evaluation is say heuristic. These are some things that we can use as evaluation, but it need not be evaluation.
Uh,
Evaluation is like just defined as a
can
function.
you explain like the term that you use, heuristic or something? Because I don't think it was specified in the uninformed search.
Yeah,
That's why.
heuristic is something that we have not discussed. Like that is coming like
Okay, it'll be
we are
discussed.
moving on from the this topic. It will be discussed. But
Okay,
evaluation is a very general thing. It
okay.
can be like depth or something. Like yeah, there are some possibilities that I write. So you can your evaluation might be the depth of the node. Your evaluation might be the cost from starting to that node, particular node. The cost of n from start. This might be one of the evaluation. Your evaluation might be cost of goal from n. This is also a valid evaluation. So you can design anything. You can say your evaluation is say 100 minus depth
I
of
didn't
n. Like,
understand the third point, like cost of gold from an. So we know the goal node. So the point is to find a path. So that is what we we can understand from that.
yeah, means the cost of the goal, like from this node, if I am going to the goal, what will be the cost? That is what I
Oh,
mean by this.
okay. N to goal. Okay, okay.
From yeah, end to goal. Yeah, you can say end to goal. This is from start to end. Like you can define your own evaluation function. It might be anything, but this is the criteria. Like this only like only definition that you can give to evaluation function is criteria to difference. This is the only criteria. Like it can be other than that. It can be anything. And this is a function of n. This is a function of the node. These are the only two criterias. Otherwise, it can be anything. It can be a constant also. You can put a constant thing like you can put like ffn is a constant. Then you randomly you will be taking something outside. Then it will be like a Bellman for you. You have to repeat it like v minus one times. So that is what an evaluation function is. So you can define anything, right? So but most of the time there are people use like depth of it. So in this case, what happens when you use depth as evaluation function? This is like the first case I want to discuss. So anyone has any idea like if you use depth as an evaluation function and you are each time when you're selecting you're choosing depth lowest depth. So what will be that algorithm?
BFS.
Yeah, it will be BFS, right? It will be BFS. So now you can uh now that is one thing. Now I can say my evaluation is cost from start to end. So in this case, what will be the algorithm?
Uh, the uniform cost search.
So in this case, it will be uniform cost search, right? So any algorithm that you come up with, right? Any AI search algorithm, you can think of as minimizing some evaluation function.
Yeah,
Like
fine.
any AI cost algorithm is minimizing some evaluation function. So it is not specific thing. It is like very general thing. Just they named something called evaluation function just so that we can talk about it. There is nothing new actually. So now one more thing that we can use is now we will come to heuristic function. Heuristic function is like this is an estimation. So this is actually first thing that you have to take care is this is an estimate. This is not the true cost. This is estimate cost, not true cost. And this is the cost from your current node to the goal. This cost is what is a heuristic function. So and one more point I will say is this is usually like a distance measurement, like a distance, some measurement related to distance. So for x, like might when I tell like all these things, you might not be like, so that's why I'll come up with an example. So imagine like you are like a this is like a pond or something. This is like a pond. You are like a frog here. This is like a frog, and this is like you have to go to like this is like your some yeah, this is like your house or something, and there are like say some what do you call this, some
Stones.
like water lilies or something.
Oh,
Yeah, you
lotus.
have lotus leaves or something, and you have to like go here. So you don't know what is this distance, right? Like like there will be like a particular sequence that will be minimizing the total number of gems or something, or total
Can we say similar to hill climbing or something like that?
yeah, hill climbing is like a special case of this. Hill
Yeah,
climbing is
because
like
like when you climb the hill, or so you will actually have like which is the easiest thing that you can hold at that point of time, and then but you don't know exactly where you're going. So I
yeah
mean,
hill
I just came up with an example.
yeah, hill climbing is like a
Not just hill climbing,
special.
just mountain climbing or something. So you just look for the easiest path at that point of time, and then you just go.
Yeah, that
Trekking.
is hill climbing is like a special case when you look at only one next obvious thing, means next easiest thing.
Okay.
Like if you're okay, I'll come to hill climbing, but in this example, say if this is you are estimating that this is say 3 meters from your house. This is say 2 meter, like say it might be some yeah 2 meters, or this is say
So this
some
is
1 meter.
actually the distance from the leaf to the house. Okay, I
Yeah,
I
this is
thought.
like this is like an estimate.
Oh, okay, okay. I thought okay from the frog to the leaf. Okay, sorry.
No, that is cost actually.
Oh,
That is the fourth
okay,
thing that we are going to cover. So this is like from whatever node you are going to jump to, from there
okay.
how much is the distance? Like this is this measurement. This is like heuristic
How
of.
do we know that actually? Like,
Yeah,
is there?
we don't know that for sure, right? So we use a
Yeah.
approximating function. This is like a that is why it is called an estimating function.
Okay, okay. That's a different subject to all to itself. Like the
Yeah, yeah,
estimating. Okay,
yeah. So one estimate might be like the Euclidean distance, like root of say if this like if you know this node as say if you know the xy coordinate of this node, you can like you know the xy coordinate of this thing x0 y0. So you'll do that thing, right? X0 x1
yeah, understood.
whole square plus y0 y1 whole square. Like you're calculating this distance.
Got it. Yeah,
Yeah, but this might not be achievable actually. It is only an estimate because ideally you have to travel like this, right?
correct.
This will be greater than like the actual cost might be greater than heuristic, or it might be less than heuristic also. It can be anything, but you are estimating that it is the Euclidean distance.
Okay.
So yeah,
Yeah,
this is like Euclidean norm or something. So how do I represent this? Yeah, something like this. So the xg is like goal, and x is cap is like your node xn, like your current node. So the Pythagorean distance between your goal node and your particular current node. So that is like an estimate, right? That is an estimate of how far it is actually. This usually these estimates are used when you have like a grid problem or something. Say your goal is here. Say goal is like 7, 8, and you only have say finite set of nodes. You don't have entire grid. You only have a finite set of grids. This is also starting point. So it is connected like this. Yeah, imagine if this is your entire graph. This is entire graph. This is your goals. This is your goal state. and this is your start state. So each point will have its own x and y, right? You don't care about this cost actually. There will be a one cost here, cost 2, cost 3, cost 4, cost 5, something, cost 6, cost 7, cost 8. There will be cost, but you don't care about the cost. What you care about is on average what is the how much far away your goal is from from the current node. That is like a Euclidean heuristic. This is only an example for a heuristic. It is not. I'm not saying that this is the only
Yeah,
heuristic.
understood.
Yeah. So whatever way you have to estimate, right? Like any estimation is fine. So most common is like say Euclidean, and then there is taxi cab.
Manhattan.
Yeah, taxi cab or Manhattan, whatever. Like both are same actually. Taxi
Oh,
cab distance or Manhattan distance. These are same things. Means that is like the you are adding up the only the components actually. You're not squaring it.
mm, mm, mm.
So these are actually heuristic functions. So it might not be distance related also, but mostly it is distance related. But it might not be distance related also. Can you like anyone think of an example like where it might not be distance related?
Time related or something like that.
Yeah, it can be time related or like yeah, it can, like specifically can you think of any example like think of any particular game or like any
So
simple
maybe
example is fine. Like just to make sure that you guys understand, I guess.
uh, shooting example, something like that.
Shooting.
Uh, so maybe like in uh, I'm just thinking a random example. So maybe in next 5 seconds there will be an enemy coming up, or next 7 seconds there will be an enemy coming up, something like that. So we are actually like thinking that. So I might be wrong. So I'm just thinking of that.
Yeah, I cannot relate to how that would be a example, but let me think of like one example. So like again, let me take chess for
Can I
example. So
try?
yeah, you can try.
So I don't know, I'm not sure, but this is my reasoning. I think chess is not something that's related to distance based because we will fix the distance like the depth.
Yeah. So in chess, when you think of a heuristic function, it is not something related to distance. So uh, in chess, like what is heuristic in chess actually? That is the goal is to checkmate your opponent, right? So from your current position, how
Exactly.
how likely it is to checkmate your opponent? That is like a probabilistic interpretation, right? Like from distance, it went to probability. Like so,
Okay,
your heuristic
you
can
can
be
do
anything.
these things. Okay, you can do
Okay.
these things like for example you are at a particular position and you're having a goal mate. So I mean it's a very straightforward thing, or it's a different, I mean like a different subject altogether. So
Yeah, you
that's why I
can
was
you
like,
can make your own heuristic function. Means even getting a correct
no, I'm just
heuristic function
asking,
might.
you are in a particular position and then you want the ultimate goal is to checkmate.
Uh,
So, with considering the number of different positions that you have, so how do you come up with a probabilistic model? I mean, I'm asking, is it a simple thing or it's a very complicated thing?
yeah, it is a very complicated thing, but you can choose a very simple thing also. Heuristic function does not limit you in saying that it has to be an accurate probability prediction. It just has to be indicative. They are not
Okay,
saying that heuristic function is not limiting in the fact that it has to be very accurate to the actual probability or something. It has to be close to the actual cost or something. Even if for the majority of the node it is following, that is a
can
good
we
heuristic. For
can we
example,
say like this
uh,
strategy games or strategy related to games? So for example, our end goal, say for example we are in a situation in a cricket match where it is like all the 9 wickets are lost and there's just 1 wicket left. So which bowler will you choose? So that, can we say that as a heuristic, considering the fact, or I mean I'm just coming up with examples related to that. So given a
okay, so
situation.
let me clarify one thing. Like heuristic is actually one type of evaluation, right? So where we started from, we like we wanted to check what are all the possible evaluation functions that I can use. Like heuristic is
Mm-hmm.
the subdivision of evaluation function, right? That part is clear,
Okay.
I think. Like it is part of a search problem where we are deciding which element to deference first.
Yeah,
That is
actually,
that is
like
what
what I
evaluation
was
functions
trying
do.
to, yeah, actually, like for example, for the ninth wicket, I'm thinking there are five bowlers, and for each bowler there will be an evaluation function written, and maybe I can say that as a heuristic, right? So, for example, for bowler one has a, the lowest thing, bowler two, bowler three. So depending on that, you are choosing the so from the bowler to the goal node, you can relate that to as a heuristic, something like that. So
Yeah,
I
you
was
can
just
relate
thinking
it
that.
as a heuristic if you like make the problem of choosing your bowler as a graph problem. Like if you can make that as a graph related problem, then going to the next bowler is like going from one bowler to another. Is like a graph going from one node to other node. So in that case, you can like think of that as a valid heuristic.
Yeah, so that's what I was saying.
Like let me give one example in chess. Maybe it will be like throwing some light. So like if you have a particular board, say board position, say the x is your board position, or say x1 is your board positions, and now your goal is to checkmate your opponent, right? Checkmate is your goal. So I am defining, like, this might not be a good heuristic, but I am defining as my heuristic as number of
Check as checkmate.
number of opponents pieces minus number of my pieces. Like this is like very simple like crude definition I'm saying. Like on like
Yeah.
this is like on average.
Uh, uh,
On average, if opponent has more pieces than me, like if opponent has more pieces than me, I am very far from winning, right? I am very far from checkmating. But if I am having more pieces than opponent, then it is closer to winning, right?
uh,
So
yeah.
this can be thought of as a heuristic. This can be like a heuristic, right? Or in
Mm.
Pac-Man, it might be like,
Can this be a heuristic, like a very dumb heuristic, like
yeah,
if
it'll be a very dumb
that is
thing
a
that they use, like, but it is a heuristic.
no, like for example, I'm saying a heuristic where like if you create a check, then that's a checkmate. That's the dumbest heuristic, but I'm just coming up with a heuristic.
Yeah,
If
you
you
can
create a
think of a
check,
heuristic number of checkmates possible, number of checks possible from node N. Yeah, this is also a, like dumb heuristic. Like this is also you can define it that way. So if you are using this heuristic and using a training a chess program or something, it will try to go to positions where there are a lot of checks.
mm,
It will like positions with a lot of checks. Need not be checkmates, but whenever there is a check, it will take that check. Okay, like any check. If you can take a check, then it will take that check.
yeah,
This version of the program will be peace hungry. It does not care about winning actually. It cares about like maximizing this thing. It means minimizing this thing. It only cares about minimizing the piece difference. This cares about like maximizing the number of checks or something. So like
yeah.
say in like another game maybe, say in Pac-Man, what is the goal state? The goal state is I have to eat all the collectibles, right? All the dots I have to eat. So in
Mm.
Pac-Man, a heuristic might be number of dots left in a
Number
particular
of
position.
successive dots. Number of successive dots.
Successor dots. No, you are evaluating for the current position, right? So that has to be a function of
Oh,
the current position.
yeah. From the current position, I have two consecutive dots. Then I mean, like,
Yeah, you can think of that also, like number of neighboring dots or something. That is one heuristic. You can think of one heuristic as number of dots remaining in the entire board. Like this is also a heuristic.
mm-hmm.
Like because if this is a heuristic, then you will obviously go to somewhere you can eat, right? Because when you eat something, number of dots remaining will go down.
Yeah.
Here what you'll do, na? Here you will go to a dot, like suppose this is also valid heuristic, but the problem what happens, right? Suppose this is the like say your Pac-Man is here. It will go here
Okay.
actually. It won't eat it. It will go here.
No, I'm saying like okay. I'm saying like uh,
Like your Pac-Man
how
is
do you
here.
say like it goes through that way? It can go to right or left, right? Like why should it go straight in that case?
So say
I'm saying like
yeah,
if
this
there
is
are
your
consecutive dots, then what I mean is like there are a lot of clusters. So in small movement, you can eat lot of dots. So that is what I was meaning.
so let me like you might be right, but let me try this. So this is a heuristic, right?
Okay,
So this is like the if it will try to minimize this.
okay,
Like your next node is trying to minimize this heuristic. You're choosing your next node to minimize this thing.
mm.
So you're like okay, it'll be like going away from dots, right? Okay, I don't want dots. I'll go to the square. I want to minimize number of dots. Remember
How do you
remember
say
this.
how are you
You,
saying it's minimizing? I'm not saying like that. So move towards the space which has like more cluster of dots. So that is what I
you
was
have
meaning.
to you have to say it as a minimization problem. Heuristic should be a
Oh,
minimization thing. Like
oh,
because
okay, okay,
because why? Because you are when you're evaluating a heuristic and you're giving it a particular numerical value and you're using that value and putting it in the fringe, right?
okay.
Or yeah, you can do it as a maximization problem also. But you
Here
have to
like
then
it
use
is
a
it
max heap. You have to
any
use a max heap. That's all.
anyway it is going to minimize, right? It is going towards the cluster which has most number of dots. When it eats the cluster, it is going to minimize, right? So I'm just thinking in that way. I might be wrong, but that is what I'm just thinking.
No, it does not.
So
You are not motivating it to eat, right? You are motivating it to stay near dots.
no, I'm motivating it to eat the dots which has lot of clusters. So if there are say three different clusters and the I mean the second cluster
Okay,
has
okay. So
lot of
let me
dots, then move.
let me take this case. So this is one cluster here. This is one cluster. So this is your Pac-Man.
Hmm.
Yeah, you're right. Suppose you're trying to maximize this. Okay, neighboring dots. You're trying to maximize this. So you will go here actually. You will go here, but if you eat this, right, your number of neighbors decrease by one, right?
Oh, okay.
You will stay.
Yeah.
You will go like this. You will keep on going like this. You like to stay near dots, but you don't like to eat them.
Okay. So I mean, I'm not right. I mean, I didn't understand how do you define a heuristic then.
No,
So
this is a valid heuristic. I'm not saying this is not a heuristic. This is a valid heuristic. This is a heuristic, but it is dumb actually. That is what I'm saying.
okay.
Like heuristic is need not be perfect also. Like this is also one way to like this. I am not saying this is not a valid heuristic. This is also heuristic. This is also heuristic. But I am saying the problem with this heuristic.
So okay.
Like if in an exam they ask, is this a valid heuristic? Yeah, this is a valid heuristic. As long as it is a function of the current node, as long as it is assigning a numerical value to the current node, it is a valid heuristic. And it should be estimating your distance to the like goal.
Okay.
Some measurement. Like it can be a bad estimation. So this is what I would say is a bad estimation. But as just because it is a bad estimation does not mean that it is not a valid heuristic.
Okay.
Okay, like do you need any additional like clarity like what is a heuristic?
From the it's an estimate from the node to the goal node. So
Yeah, it is an
maybe that.
estimation from end to goal. That is first thing. It is a type of evaluation, and it need not be perfect also. Like this need not be equal to the actual cost.
So can we say, heuristic function as a subset of evaluation function?
Yeah, it is a subset of evaluation function.
Okay.
Now like
So evaluation function is a very general thing,
yeah, evaluation
and
function is
heuristic
general thing.
function.
They need not even name something like evaluation function. You can think of evaluation function as the, like, instead of saying there is a way, like there is a strategy to choose the minimum, right? They are naming the
Okay.
strategy as evaluation. Like each time if I have to say, think of the strategy to choose the minimum from the fringe, think of the strategy to choose the minimum from the fringe, instead of that they have given a name for name for that particular statement. They're told that that is a evaluation.
Okay.
By naming that as evaluation, they're not limiting anything, they're not restricting. They're not saying that it should be the estimate of the cost. They're not saying that it should be any, they're not giving any meaning to that. But when you're saying it is heuristic, additionally they are giving a meaning. Okay, this is now an estimate on how far away it is from goal.
Yeah, understood.
And it can be a bad heuristic also.
Yeah.
Means it can be very bad estimate. Means for near, if you are going nearby to the goal, actually the heuristic function may increase also. Means it is actually a very
Mhm.
bad heuristic, but still it is a valid heuristic as long as you are saying that it is a estimate. That is my estimation. As long as you're saying that that is my estimation, it is a valid heuristic.
So you are saying the heuristic might say one thing, but the actual thing might happen
Yeah,
the
might be
other way.
different. Yeah, but the actually, like, this is your goal, and these are like your nodes. These are like your goal nodes. This is your goal, and these are your like your intermediate nodes. This is like, say, u v w. So h of u is saying 1, h of v is saying 2, h of w is saying 3. This is also valid heuristic, but it is not. It is not like this is a bad heuristic. That's all.
Yeah.
But it is a valid heuristic. So what would be a good heuristic? Like h of w is equal to, like, say, 1,
One.
h of v is equal to, say, 2, h of u equal to, say, 3. This is like a good heuristic, but both are heuristics.
Okay. Yeah, understood.
That's all. So now moving, like, going to the first informed search algorithm, that is called greedy best first. So think of the general thing, right? Where is the general algorithm? Yeah, this is the general thing, right? The pop the node from the fringe. So what you will do, like, initialize fringe with start node. Then this is your iteration step. Defringe the lowest heuristic node. This is your fringe. You have, say, some u, v, some nodes up to n. Here you, and they are having a value, right? U of, say, 1, v of, say, 2, like some values associated with every node, and you are choosing the lowest value heuristic, and you are popping that outside, and then you are goal testing, and then after goal testing, if it is the goal means exit. You are exiting the search algorithm. If it is not the goal, you are continuing to the next step. So here, what you are doing, here you are generating successor. Generating successor is also called expanding. Some people might use expanding the node. Yeah, big data structure people use expanding the node actually. 4 is like evaluating all successors and adding to fringe. Yeah, this is your entire, like, this is your loop. You loop through 1 to 4. This is your entire greedy best first search.
Okay.
So, like, the only thing is here evaluation is equal to heuristic. Then it is greedy GBFS means greedy BFS. Evaluation function usually they denote E of n. This they usually denote H of n. So E of n is
Okay.
equal to H of n. This is like the only like this is like very general thing, but still you can maybe we'll take an example, then it will be clear, I guess.
Yeah.
Let me take an example. Are you able to see the screen now? Like I switched to the laptop screen
I'm not able to see the screen. Laptop screen.
right now.
Now I can see.
Okay, so this is like a graph only, right?
Yeah.
And like nearby the graph, like outside the node, right? What is given is like the heuristic value for that particular node.
Okay.
Think of it like that. Like this is like the heuristic value for that particular node. So
Hmm.
and think now like think of how the greedy best first search will like work in this graph. Like like the algorithm that I've discussed, right?
Yeah.
So think like it
So
try to think like if
we'll
you
go to
want time you
five.
can, yeah, you can try
Yeah.
to work it out yourself and then come back, or you can like solve it right now.
Okay, so I'm just saying it by word. So for
Mhm.
first, it will actually take the, I don't know what it is actually like, the name. Okay, A. So it will actually put A in the fringe.
Uh,
So once it puts A in the fringe, and then it will goal test. So first we need to know what is the goal here. So uh, I don't know what is the goal here. Which
yeah,
node
but
is the goal?
yeah, you think that there is no goal, like
Oh, okay. Then without goal, how do you do goal search? Like,
yeah, your goal test will fail. That's all. Like your goal test will fail every
or
time.
okay, okay. So then, so the goal test will fail. So it'll see which has the lowest one, lowest heuristic. So D has the lowest heuristic. So it'll go to D. From D, it will check which has the lowest heuristic. What it'll do is first it'll generate the successor functions, and then it'll add it in the fringe, and it'll say J has the lowest heuristic. It'll go to
Okay, okay, okay.
J.
Let me pause. Let me pause. So you started with A, right?
Yeah.
So A is not your goal.
Mm.
So you generated the successor for A, right?
Yeah.
So all of this is now in the fringe. B, C, D,
Oh, okay.
E. Everything is in the fringe,
Okay.
right?
Yeah. So that
Yeah,
is very similar to how we do UCS. So,
yeah, it is very similar to how do we do UCS. Just
okay.
instead of looking at the cost, we are looking at heuristic. That's all.
Okay. So that means then we will search B. We will actually defringe B, and then try to expand them. So the if I were to write it, so then the fringe will have like C as C7, E8, and then we have expanded D. So D will have like I will have 15, J will have uh,
No, no, no.
14.
One more thing is evaluation function is not like you don't
Co-
have to add like add carry forward your heuristic. Heuristic
okay,
function is just a function of that individual node. Like h of I is 10. You only care about h of I.
okay, okay,
You
fine.
don't like
Now I'm
when in UCS you add, right, because that is the
okay.
cost from like in UCS the evaluation function is the cost from start to that particular node.
Okay, okay.
In UCS what is happening that is
Okay,
evaluation
okay,
function
so
only, but it's
okay,
like a
yeah. So
cost.
they've already given it from that node to the end node, so we don't have to do it. Yeah, fine.
Yeah. So this is like
So
you don't have to add it. That is the one thing you have to keep in mind when you are using a heuristic. It's like
so
UCS and
the
GFS.
next
Uh-huh.
yeah, so the next node will be different will be B, and the next node that will be different will be C, and the next node will be different will be E. So all the level one nodes will be different. So you have a tie between I and H. You have L. You have L. L will defringe, and
Hmm.
then once L defringes, uh, X will defringe. Once X defringes, W will defringe,
Hmm.
and once W defringes, Y will defringe.
Ah,
Then
yeah.
once Y defringes, it'll actually look for like maybe it'll defringe J, I guess. So it'll defringe J, and once it defringes
G comes
J,
before,
it'll
right? G comes before J, I guess.
where is G?
Let
Okay,
me.
G
Where did
comes.
you reach?
Yeah, J is because I thought J because D was actually the one which actually defringed first. So maybe I took
Okay, okay, okay. Yeah,
that as
yeah. Yeah. In that, if it is like if your data set that you are using, right? If it is in
uh,
place, then it will go to G only because you popped that, you have pushed that first, right?
okay, okay,
Means tie breaking, how that needs to, you need to define how you are breaking tie.
okay,
That is not defined in this question, right? So there are two methods you can do in that lexicological order. You can break the tie, or you can use the last in first out philosophy.
okay.
So last in first out, it will go to J actually.
Uh, uh, no, first in first out means J. Last in first out means it'll
Yeah, yeah.
be
Sorry, last in first out will be G. Yeah, first in first out. So like if
uh,
underlying fringe is a priority queue, and the
uh,
priority queue is actually in place. If that is the case, then it will go to J.
uh,
Not in place.
yeah.
So I'm not saying in place. Stable. If that particular thing is stable, right?
Okay.
Stable in the sense,
Stable means maintaining the
like,
order.
yeah,
If
maintaining the
the
order. If when they're sorting something, if they are at the same value, then what I inserted first has to come first.
so that's first in first out.
Yeah, yeah, that is first in first out. So
Okay,
that in that case, look, it depends on the implementation detail, right? Like what data structure they are using for the fringe. So it is very sensitive to this thing. So when someone
yeah,
says no, G is correct, J is correct, that means like the underlying, it is very sensitive on the underlying implementation.
yeah.
Yeah, it is very
Definitely.
sensitive, like minimum heap, right? Min heap. If you are using
Hmm.
a min heap, it is not a min heap is not a stable data structure, right?
Yeah.
Means you have inserted something very first, but it might appear at the very last also. Like if everything is same, if everything has the same value, it is not in place. But if you are using,
So
say, a different data structure, it might be in place, or it might be like using, if for tie it might be last in first out, or for tie it may be first in first out. You don't know, so it depends on implementation. So unless they have given something in the question, given something in the question, you have to assume it is like alphabetical order.
okay, okay. So then G will actually pop, and then once G pops, like O and O and P will defringe. So once O and P defringes, J will defringe and T will defringe. Once T defringes, H will defringe, and Q and R will defringe. Then I will defringe. Then S will defringe. Then F will defringe. Once F defringes, N will defringe and M will defringe, and then K will defringe. Uh, After K defringes, U will defringe and V will defringe. So this is the order, I guess.
Yeah, like you can just check it with this order. Like yeah, you basically like the last three things you said correct, I guess. Like
Yeah,
I don't listen to the
NM.
entire thing, but maybe it is correct.
Okay, yeah.
Yeah, up
I,
to G it was correct. I was following,
yeah, I
but
followed till NM but then I don't remember the other things.
okay. So
Before
this
NM,
is,
it will be F, yeah. So F also will be right, yeah. I guess it's correct. I guess.
so that is how you, when you give, when they give a question like graph, given graph, they might not give this heuristic in a like adjacent to the graph. They might give this in a table.
Uh,
This heuristic thing might be given in a table. Let me see if I can. I can show a question like where the heuristic is given in a table or something. Okay, in this particular note, they have not mentioned something. Yeah, let me see if there is something where it is given a table. Yeah, they can give something like this also. Like what I mean by table is they can say that this is my there I am using two heuristic functions. This is my h1 heuristic. This is my both are heuristic functions. So they can give
Okay.
the question in a table format also.
Okay.
They will give the graph edge cost with edge cost. So I don't think you can see. Look, they will give the graph with the edge cost. This is like the
Yeah.
cost.
Yeah.
This is not, it's not a heuristic.
Yeah.
And then they will give two like one table. Like this is one of the possibilities, one of the possible heuristic. This is one of the possible heuristic. So now they will ask some question. What will happen if I use h1? What will happen if I use h2? Like they might ask in a table format also. It might not be always like a graph thing.
Okay.
Actually, that is something that you have to keep in mind. They can come up with different methods. Like in what is inside is like a heuristic. What is outside is like the edge cost. Like any format, they might give the heuristic. It might not be like some fixed thing. There is no particular
Yeah.
notation that they follow for heuristic. It can be a table, it can be a graph, anything.
Okay. Understood.
Understood, right? So let me go to this particular example. So in this example, right? Okay, this is a beam search example actually. Yeah, this is what I was saying actually. Okay, in this graph, right? Like
Mhm.
I'm like for making a particular point, I want to I want you to focus on this graph actually. S is your starting node, G is your goal
Okay.
node. S is
Okay.
your starting node and G is your goal node. So now if you are doing this thing from doing the greedy best first search from S, like what will be the sequence? This is your heuristic. This is the heuristic that you're using.
So from yes, you have like only A. So you can go only to A from S.
Uh,
So uh, so from A you have like B and D. So from to B it is 1 and to D it is 4. So you will go to B. From B you will go again to A. From A again you will go to B. So you will be stuck in an infinite loop if I'm not wrong.
yeah, this will be a loop. So this is like an example where greedy best first search is not complete. It is not optimal. So
Okay.
like you can think like we can like memorize a graph where, or you can even think of even a simpler case than this where you can think about this or you can memorize this to argue why BFS or greedy best first search is not optimal or not complete.
Yeah.
This is like a
Understood.
what you say. This is like a argument against completeness,
Yeah. Understood.
and this might be a good heuristic also. This is not
Hmm.
like a bad heuristic. So think of this as the geometric distance to goal node.
Maybe the strategy that we chose might be not right. We can understand it that way.
Now,
The
even if it is a
heuristic
good
is,
strategy, even if I have a good heuristic, this can happen. That is what I'm
yeah,
trying to convey.
the heuristic is good, but the strategy is wrong. Maybe that's why it
Yeah.
is.
So because like say if this heuristic is like closeness to goal node, closeness to goal node, physical closeness, not like the edge closeness. So B is the closest node to goal, right?
Yeah, but
B
you
and
don't
D.
have like anything.
Yeah,
It's
you
a
don't
bad
have an edge.
heuristic.
You don't have an edge right here. That is the
Yeah,
problem,
this is
right?
a
If
bad
there was an
heuristic.
edge, yeah, it was a no. It was a good heuristic, but it was like the it was not it was a heuristic, but it was not like good
Okay,
estimation of
it doesn't have edge. Okay, it doesn't have an edge or a path
yeah because
towards.
yeah, you cannot given this node like this is a small node, okay, that is why you're able to say it is a bad heuristic. Say your goal is like this is like some after some 3 5 like some
No,
10
no,
nodes.
it might be a good heuristic. Yeah, I correct myself. It might be a good heuristic, but it doesn't have a path that is. I mean, the reality is not.
Yeah,
I mean,
reflected here
matching it.
there is no path there. So think of like let me draw an extreme case. So right now are you able to see my tab?
Yeah, yeah.
So think of this is the goal node and this is like say B and this is say D and this is say some k or something, and there are so many nodes in between. So like your heuristic is, and each of the thing is having say some xy value like xy, and this goal is having say some x naught y naught. You are using a distance measurement. Like this is your, you're using a distance measurement for, this is actually not a node. You don't know whether this edge is there,
Mm.
because think of the function, like when you're implementing a heuristic function, right? You only have node values, like you only have x y x naught y naught. You only have this thing. You don't have information whether there is an edge or something. So you're trying
Mm.
to estimate the cost with
Yeah,
this
yeah, yeah,
information.
yeah, yeah, I understand that. Yeah, I
So there
totally
is
understand.
no even if a good heuristic you to design, it might be like a bad, like even if this, like this is the condition, but there is no like edge between these two things. This might be the graph. The graph might be this also, but the only way to the goal is through D.
Mm.
This is like the
Yeah,
only way through to the goal, but your heuristic is not able to understand that, right? It is not the,
yeah.
it is not a heuristic problem. It is like your evaluation problem. You are relying only on the heuristic to get the evaluation. So your evaluation is equal to h of n. You're not adding something else, right? You're not using some other information. So that is the problem actually. The heuristic is not bad. Your evaluation is bad. You can say your evaluation is bad, but heuristic is good.
Okay, understood.
And this is why, like one more thing, this is why greedy best first search is not optimal. It is not complete, and like it will have loops also. It will have loops in the sense like you can like go back and forth between A and B. Now
Yeah.
think of this example, like think of this particular example, like a very simple thing. Like from
I
like
couldn't
think
see
of,
it.
oh, okay, okay, let me see. Okay, okay. Now
Yeah, 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 I can see.
like what will happen in this particular situation? Can you think of which
So
path will be
first we'll
returned?
start. Yeah, start A, and then uh, heuristic is 3. Uh, yeah, so it'll go to start A, B, C goal. If,
Like how you came up with ABC? ABC the
because
optimum path.
no, no, I'm not saying the optimal path. I'm just taking the heuristic path because, like, from
From
A,
A, A,
okay, yeah, from A it can go to C. Okay, okay, sorry.
yeah, because
From
you
A it
don't
can
care
go to
about the edge, right? You don't care about the edge.
yeah.
You only care
So
about,
from A
okay,
it
C
can
is
go to
getting,
C.
C is closer to goal.
Yeah. So from C
So
to
what,
zero. So
so what
start
happened
A,
here?
C.
What happened here? You ignored the cost. You just want to reach nearby the goal. You are only caring about how much close I am to the goal. You don't care about what is the cost to get there.
Yeah, yeah,
So like you are ignoring path cost. That is the limitation of greedy west first search. Actual path cost to some node you are not taking care of. That is why you are not reaching an optimal solution. You can like the greedy best first search will return this path. Start A C goal. This is the path returned by greedy best first search. But in fact, there is an even optimum path A B C D or A B C goal. This is an even optimum path, but it is not taking that path. So that is like an example why greedy best first search is not optimal.
yeah.
And heuristic function is
And
not bad also. Heuristic function is correct only, good only. Like C is closer to the goal, so C is having 1. B is
yeah,
somewhat away from the goal, so B is having 2. A is the farthest away from the goal, so A is having 3. Heuristic is also making sense, right? Heuristic is not something very bad. It's a logical heuristic only, not stupid. So even with a non-stupid heuristic or like even with a good heuristic, greedy best first search is not the correct algorithm that we have to use. That is what I want to convey in this.
yeah. Understood.
So there are two extreme cases of like before moving on from heuristic, there are two extreme cases of greedy best first search. Yeah, before that, let me think, tell you the complexity. So let me tell you the time complexity. So what is worst case, right? In worst case, it will behave like a depth first search, right?
I couldn't.
Like very bad heuristic, it will search everything. Like worst case. Worst case behavior will be, sorry, not depth first search, best first, breadth first search. Worst case behavior of the greedy algorithm, right, will be equivalent to the
uh,
best breadth first search.
yeah.
So this is like the time complexity and the space complexity. Both are equivalent to the breadth first search. Like this point, are you like clear or like any further thing?
Uh, yeah, bro.
Okay. Now, so now we have to like move on to beam search. So beam search is a special case of, like a special case of this thing, greedy algorithm, where like only difference, right? The entire algorithm is same. This everything is same. So I'll copy it. I'll copy the entire thing. I'll copy everything. Like, but the only difference is your fringe is limited size. Fringe is limited size means this is like say only k nodes you can store here. So
Okay.
beam search of k. You only have k slots actually here. Think of like that. Evaluation function, everything is the same. Like it is heuristic only.
Okay.
Evaluation is the same, but you can only, like if you generate successor, right? You're generating
Mm.
successor, right? You generated maybe 10 successors. You only
So
have
the
space
top
left for two.
minimum. So if
Like
you have
maybe,
k is equal to 10 means you'll store only the 10. I mean, like
yeah,
it just
whatever space is left.
yeah. But when you pop out one thing, then you'll have one space left. The one space will be occupied by the least one, something like that.
So what happens? Like suppose already it is full. Suppose already it is full. This is case one. Case one, it is already full. So you know what happens when you pop, right? When you defringe, right?
Mm.
One slot will be free.
Yeah.
At least like one slot will be free. So like at minimum you can add one, right? At least one successor you can add.
Maximum you can add one.
No, like so it might not be full also. Say the fringe is only having three elements.
Okay, then yeah.
So
If
the
there are
minimum,
no elements to add, then what you will do, bro? For example, if there are no, then minimum elements can be zero, right? So if there are no elements to add, so I'm just taking.
yeah, no
Will
successor. You're saying no successor.
yeah, then
Yeah, then you're
okay,
not restricted by the fringe, right? Like the fringe is having. I'm saying talking about the restriction of the fringe. Like fringe is
okay,
restricting you, saying that sometimes it will allow you to only add one successor. You
okay,
might not have one successor. That is another case, but it might limit you to say you cannot. It cannot say okay, you don't have a successor. So at least one successor it will allow at any
okay,
point,
okay.
and at max it will allow k successors. When that will happen, when the fringe is like,
Empty.
when it is completely free, like when you, there was only one element, you popped that element, you goal tested, okay, it is not a goal, you throw it away, you generate the successor, you got 10 successes, okay, now you can add everything.
Yeah.
So in the greedy best first search, you can think of it as beam search with k is equal to infinity. Like
Mm-hmm.
greedy best first search is like k equal to infinity.
Yeah. Okay.
Now if you put k equal to 1, that is your hill climbing search.
Okay.
Understood, right? So like let me compare
Why
three
are
things.
why is it analogous to hill climbing in the sense like I didn't
Yeah.
understand.
So at hill climbing, why is analogous? So any node here you could not say like how many successors it will have. Like at least you could say at
Yeah.
least one, at most k, right? In hill climbing, it will be exactly one. Like every node will get exactly one successor if it is having a successor. Like every node will get exactly one slot.
Okay.
So like I'll show example. So uh, I'll show one example actually. So yeah, are you able to see the screen?
Yeah.
So in this, what is happening? Yeah, this is the graph. Like try to do the beam search with k equal to 2.
Okay. So it will come to C, and from C it will see. It'll go to. Uh, it'll take T and O as its fringe, and then it'll pop T, and it will actually have nothing to add from T, so it'll add a B into it. So it will have O and B. So it will pop O, and it will add I, and it will pop I, and it will add Z. Am I right or wrong?
Like at no point is b added to the fringe, right?
Yeah.
B is not added to the fringe, right? You like let me draw the graph here so it will become. I thought you said B is there at some point. So that's what I want to clarify.
So T and O are the only ones which are.
Yeah. So the that is like the property of beam search. Some subtrees are not even explored.
Yeah.
So this is having further I, and this is having further I. So let it be like any subtree. Like these are having like let's say any subtree. Don't care about this. This is
Mm-hmm.
this is your like say set. So now like initially your fringe size is k. So beam search k equal to 2. You only have two slots. Now you started with C, right?
Yeah.
And evaluation of C was say 21. Yeah, so you see you added C equal to 21. Now you pop C because that was the only option. So you popped C.
Mm.
Pop C, you goal tested. No, this is not the
Mm.
goal. This is not the goal. So what you did, you generated the successor. You
T
generated
and O.
B, T, O, everything you generated, but you can only store
Yeah.
two, right?
Add only two. Yeah. So T and O I add.
You T equal to 5 and you stored O is equal to 7. Now at no point you are going back to B, E, F. So whenever you generated, right, you generated the entire thing. B equal to 14, T equal to 5, O equal to 7, E equal to 12, P equal to 15. But you are not able to store everything. You selected the top two. You selected the top two, put them in the fringe. The other you don't care about now. You never go back to these things.
Yeah. Yeah. Yeah.
Means the algorithm at any point, right?
Mm.
At no point it will go back to this. So it is like pruned. This is pruned. These are pruned. So now the algorithm and their algorithm scope is coming in these two trees. So
Yeah.
these two subtrees. So in this case, T is not having they will pop T. T is not having any successor, right? But what it did, one slot became free. Now what will do? Now it will pop O. Now O is popped. So here T was popped. Here O is popped.
Uh,
O is popped. Now what happened? When O is popped, both are free.
I and N will be added.
Yeah. So I and N will be again. So I is having say 4. This is having say 44 or something. So this is like say 4, 5, 4, and say 44. So now like next it will be I, and again fringe is having one slot, empty slot. Fringe is having one empty slot. One it is saying N44. So I actually reached the goal. This is the goal, and G it is having 0. So goal 0. So this will add Z equal to 0. So it will reach the goal. Means next it will be popped Z. It will stop. When goal test it will pass actually. Goal test of Z return 1. So it will return from the algorithm.
Yeah.
But now like think of the case. What if this is not a goal? This is like a dead end. What if the goal was here?
Yeah, yeah, I was thinking about that.
So what if the goal was here? So this is not complete. If it is not complete, it's not optimum. And at any level, right? At any level, like this is the say the level 0, this is level 1, this is level 2. At any level, maximum you have k slots. This is the maximum. Minimum you have one slot.
Yeah,
This is true, right? At any level. So at any
yeah.
level, like you say your goal is at level S or something. The maximum nodes that you will expand is like say S into K.
Three powers. Okay. Oh, okay, okay,
At
okay,
like
okay.
like every level you have two nodes, like at most you have
Yeah, yeah,
two nodes in the you can put in the fridge. So like
yeah.
level 1, level 2, level 3. So in 3 levels you get at most 3 into 2. This will never be the case because in some cases you will only have one slot left. But I am taking the worst case. In worst case, if there is k slots left and each level having k new children, I am having k slots left. Then in the worst case, up to well reaching the goal, I will have added. I will have checked sk nodes, sk number of nodes. So this is like the time complexity.
Space complexity. Or...
The space complexity, like space, you are limiting, right? This is already fixed, right?
Okay. Oh, yeah. Okay, okay. Sorry. Yeah. Understand. Yeah. Sorry.
Okay, okay. So, so then now I want to come to one edge case. So you might be thinking, like this is the conclusion you might be thinking. Page complexity is equal to the shallow. This is the shallowest node. S is equal to the shallowest node, shallowest goal. It might not reach the goal also, but you just want to calculate the worst case. K is equal to your beam width. So Sk. This your complexity is Sk. Now you are like thinking to write. Okay, because I only have the fringe. I only have big O say K. But the problem is this is wrong actually.
Okay.
So
Because constant.
yeah, because of k is constant. So what is happening, right? In all the other algorithms, everything like A star, UCS, BCF, what they take is okay. I have not mentioned that here. Okay, in the summary I have not mentioned. So okay, let me add that thing here. So in all the other algorithms, your space complexity is your fringe complexity, like fringe size. Like the maximum size of the fringe is there is your space complexity, but only in beam search, right?
Hmm.
Beam search, what will happen? It will not be this thing. It will not be k. It will be k times. It will be what it will be. Yeah, it will be b power m only.
Okay.
Like no, sorry. It will be k
What a,
times m. It will be k times m.
what is M?
M is like your depth actually. Depth in the sense like yeah, k times s you can tell. What
Why
s you
K
use?
this? Like,
Okay, so now this is like a this is applicable for everything actually. Phase complexity, right? Phase complexity, this is general case. Is like the fringe complexity plus space to store return path. So the algorithm has to return the goal path to the goal, right? Whatever
okay.
algorithm you are using has to return, like when the algorithm is ending, it has to return a path, like a list of nodes from the starting to
Yeah.
this, like from the starting node to the goal node. So it has to return like S, like from S I will go to G, from G I will go to. It cannot say that okay I have found the path and it cannot exit, right? It has to
Yeah.
return a list of nodes. So that means it has to store that somewhere, like the optimum path, right? All the nodes in the optimum path has to be allocated. It cannot be deallocated.
Oh,
right? But what happened in all the other algorithm, the fringe complexity was higher than this complexity. In all the other algorithms, like say DFS, BFS, like say UCS or A star, that this we are going to discuss. So A star, greedy, like in any algorithm, this was say always this complexity was always greater than whatever path complexity was there. But in this particular beam search, right, what is happening? Fringe complexity is fixed. It is k. So this is actually the other way around. This path complexity is higher than uh, this thing, like the fringe complexity. So this is like the exception. Only in this particular case, right? Space complexity not equal to fringe complexity. You can say. In all the other cases, it is valid because this is like this is having say uh, this might be big O n square. This might be big O n. So you don't say it is like big O n. You don't say it is big O n square plus n, right? You can just summarize
yeah.
it as big O n. So this was happening in the background for all the other algorithms also, but they were not proving that a path complexity is less than fringe complexity because path you returning the path is something that you have to do in every algorithm. It is not like special case with some beam search or something. That this was something that was happening with all the other algorithm because in the fringe you are not storing the path. In the fringe, what is happening? Like this is like the list of nodes yet to visit, right? This is a list of nodes yet to visit. From this, can you get the path? Can you get the path? Like you cannot get the path, right? Like suppose you goal tested. You goal tested and it returned one. Okay, I have found the goal. So how will you like from the fringe are you able to get back the path? You are not able to get now.
No, you will actually for everything you will be maintaining that, but we
Yeah,
haven't
you will
explicitly
be
said that.
you will be using some data structure like parent of for each thing you pop na, for each thing you put in fringe or pop from fringe, you will be updating a parent pointer. You will be doing something like this.
Hmm.
So suppose I am putting v in fringe. I am putting v in fringe. I will update another data structure saying parent of v is something that I popped earlier, something that generated v. Like say this is generating function. I got v. So what I'll do? I'll do parent of v equal to u. I'll add this, and this is like the successor generating function. If successor function
Yeah.
generating function is giving me some like list of say all like w x y z, I will iterate over this list. What I'll do? I'll fold all f of u for all f of u. What I'll do? I'll first evaluate for all say for all I in f of u. I will evaluate I. I will add to fringe. I will add to fringe I, and then I will update that parent pointer like parent of I is equal to u. This is what is happening actually.
Yeah.
So this thing you have to maintain, but this was like a hidden thing. This no one was discussing this because it this complexity was almost space complexity was almost negligible. Like it was like a like it was all like it will be obviously lesser than the fringe only. Fringe will grow very fast because of the branching factor. Fringe will be like
Hmm.
exponentially growing, but this will not be growing. This will be linear something. This will be something linear, and fringe will be something exponential. So no one was taking care of this thing. So that
Yeah.
is why in uh, beam search is a special case where you have to remember the space complexity is not the fringe size. This is not true. But all other algorithms you can say this is true.
Yeah.
So that is one thing. And hill climbing search is a special case. Hill climbing search there is no example given in the lecture. Like any problem state, some problems are not given in the lecture, so I'm not able to discuss any problems actually. Yeah, you can try the hill climbing search here actually if you want. You are able to see the graph,
So
right?
yeah. So from A it will go to C. From C it will go to H, and from H it will go to Q. So I mean that'll be a dead end, I guess.
Yeah, from A it will go to. Can you repeat?
From oh sorry, from A it will go to D. From D it will go to uh, J, and from J it will go to T, I guess. Sorry, I didn't.
Yeah, yeah. Okay. So what property of hill climbing search is like? When you go to successor, all the other subtrees are pruned.
Yeah,
Understood, right? This is like when you go
yeah,
here, then you're not backtracking. Like you are not
yeah,
going back. The backtracking thing is not happening. You are going like you're greedily going and dead end. Even at dead end, now you're dead there actually. You're not coming back. So each step you're making, your like say your graph is getting like truncated. Your entire graph is getting collapsed.
yeah. Understood.
And now you can do the same with beam search k equal to 2, same graph.
Yeah, so it will be D and C, and once D will be popped, so J will be added, and then C will be popped, H
No,
will
why
be
you are saying
added.
C? You cannot. B is lower than C, right? B is 6 only. Not able to see,
Oh,
or should I
sorry,
say?
I thought A. Yeah, I mean like sometimes it's showing clarity, sometimes it's like clarity is going. Sorry.
Okay. So it will have
Yeah.
B and D first. B and D will
Uh,
be stored in the
yeah,
fringe.
sorry. Now I'll say first it'll have B and D, and then from B and D, it'll D will be popped, so J will be added, and then B will be popped and G will be added, and uh, depending on the like the tiebreaker, G will be popped, and then uh, O will be added, and then O will be popped, and P will be added. P will be popped, uh, and then uh, nothing is there to add, so it will
Okay. So
pop
yeah,
G, and then T will be added, and T will be popped.
yeah. So this is like yeah, that is correct actually. So like in case, right? Like let me that particular thing let me focus, because most of the questions tiebreaker will give you different solution. So in this particular question, like the tiebreaker, how you decide, like J first or J first, G or J first. This will decide the path, right?
Yeah,
Tiebreaker is deciding the path. So most of the question, if it is not given, right?
yeah.
Most of the question is not given, and the graph is say some alphabetical thing, A, B, C, D. Indirectly, they want you to take the alphabetical order.
Hmm.
Like suppose instead of A, B, C, D, say they are given some useless information, like there is no graph. Then what you have to do, you have to follow the
First in
last,
first.
yeah, first in first out.
First in.
Because why what is the justification? Somewhere in the question they'll be given priority queue instead of the fringe, na? Instead of saying the fringe. The fringe is like a very general thing. Fringe is saying something general. By saying fringe, I am not focusing on the data structure. But by saying priority queue, I am restricting myself to the data structure. The priority queue can only be implemented in certain ways. So by default, most of the priority queue implementations will follow the queue structure.
Okay,
Queue structure in the sense first in, first out.
okay,
And if they are saying somewhere priority stack, that means tiebreaker is first in, last out, or last in, first out.
last in.
So that depends on the implementation. But like if in gate someone is saying this is not correct, it has to be, let's see, logical order, and in the question it is not very clearly written, it might be marks to all only,
Okay,
because it is very sensitive to implementation, underlying data structure that you use. Okay, so this is like what I now I guess only A star algorithm is pending.